Hello friends, good afternoon and welcome to EduSite Live Lectures. Dear friends, today in Computer Sciences, we will be talking about Wireless Sensor Networks Part 3. To discuss this topic, we have with us our subject expert, Dr. Advitya Sinha. Dr. Sinha is Assistant Professor in Department of Computer Sciences in a prominent university in NCR of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. Welcome viewers. In this third series of lecture on wireless sensor network, we'll be studying more introductory topics and lessons on routing methods. Also, we'll move on to sensing models that are there in context of sensor networking, and we'll obviously talk about some predominant mobility patterns that are inherently visible when we are talking about the sensors, especially mobile sensors. Roughly, the contents that we are going to cover in this lecture will include the node deployment, different node deployment strategies, what are the different routing techniques in support of such deployments. Then we'll come across the sensing model, what are the different sensing parameters that are there, because as the name goes, sensing is a prime feature of wireless sensor network apart from communication services. And also we'll do a small case study so that it will be user for the viewers to understand how the sensing model can be brought into use when real-time sensor network deployment is concerned. We'll take up binary and probabilistic models to understand this feature. Then we'll move on to the mobility models. We'll understand different forms of mobility, different categorization, and different types of movement in terms of is it an intentional or unintentional movement, that is whether the destination point is known or unknown prior to network setup, or is it a kind of individual movement, the sensors are individually mobile given a region of interest, or it's a group movement, that is nodes, more than one nodes, a set of nodes or a cluster of nodes are moving in a particular direction with some random speed. So in the last lecture we were talking about the significance of routing in sensor network. We spoke about manual deployment and the random deployment. In manual deployment, what happens, the location is known because the sensors are manually placed. So where these sensors are placed actually in the region of interest is known, as a result of which data can be routed through determined paths. Even the network administrators, they can decide which paths are optimally correct in terms of energy usage, or if we want our application to be delay resistant. So likewise, the paths can be predetermined accordingly if it is a manual deployment of sensor network. Now, what about if the deployment is random? If the deployment is random, it means that the sensor's localization is an important feature, as the location is unknown. So in this case, optimal clustering is required, positioning is required. So we take help of with multi-hop routing schemes, etc. Now let us see what are the different routing strategies available to us. Now on the basis of type of application, there is one categorization, because obviously there are so many categorization when we talk about routing. It's such a wide topic. So let's study the categorizations on the basis of some cases and other. So the first is on the basis of the type of application that we have. So applications can be time driven, or it can be event driven, query driven, or hybrid. So in this manner we can have different routing protocols. So say for example, if we are talking about the time driven applications, in this what happens, maybe the applications are periodic in nature, that is they are involved in periodic collection of sensors, sense data from the environment, and they have to report this data periodically, that is maybe at the end of 1 hour or maybe at the end of 1 minute, etc. And continuous monitoring is what? It's like monitoring of a blast furnace. The personnels involved in such applications, they have to continuously check whether the temperature that is required in the blast furnace kind, critical applications basically, if there is a change in temperature or with respect to time, so instantaneously the information should be reported. So this is a time driven application, so accordingly the routing protocols should be developed. Next is event driven. Event driven means there's some sudden changes in the environment, in the surrounding environment. Maybe say some intrusion detection application is going on. So some intruder is detected, and then what type of safety mechanisms should be coming up next. So it's a kind of event driven. Whenever some event happens, it triggers some kind of results. So the next is query driven. Query driven is generally found maybe in say the environment applications or monitoring applications, where if there is a change in say surrounding temperature or in the climate conditions, only then the application is supposed to get reported of the changes. So whenever there is a query floated, in such case what happens, the base station, the managers, the administrators who are sitting at the base station, they might be interested in knowing whether some threshold that is defined, whether that sensed data is crossing that threshold or not, whether it is lying within some threshold parameters or something like that. If that query is satisfied by selected sensors, only those sensors having qualifying the type of query that is being propagated, only those sensors will be reporting back. So we can see that the routing can be with respect to time, or it can be event triggered, or it can be whenever a query is given or flooded. Next is hybrid. Hybrid is something like it's a combination of above types of applications. For some portion of the network phase, it can be a time driven one, but if say some event happens, so it get prioritized, and for a certain period of the network functioning, it might be event driven as well. So different combinations can be taken up to get a hybridization of routing schemes. Now this was on the basis of type of application. Now let's talk about on the basis of network structure. It can be flat network structure, hierarchy based, can be location based, or quality of service. Flat, if you're talking about flat network structure, it means that all the nodes are homogeneous, which means that they might be similar in hardware design or maybe in the software functioning. Maybe they are given a same type of task to be performed during its operational lifetime, etc. Then we have hierarchy based. Hierarchy based, it means that clusters are formed. In flat network structure, what happens, all the nodes, they are reporting their data to the base station or sink or cluster head, whatever, the local head, etc. And in hierarchy based applications, what happens, the nodes can form close groups, and each group will have a leader or say a head node, and that head node will be performing the task of forwarding or relaying the packets further. So in case of hierarchy based, it depends upon that how this hierarchy formation is being done. The hierarchy can be formed on the basis of say spatial distribution of the nodes that are closely located with respect to each other in terms of distance. Obviously we are talking about the distance metric, then they are collaborated into a group. Otherwise it can be a clustering on the basis of temporal activities. For a given time domain, there can be some nodes who are performing same type of task, or maybe some role is given to them. So on the basis of temporal activities, there can be a formation of hierarchy as well. And obviously functional similarity throughout the domain or throughout the space. If space and time is not much of importance, it can be such that the functions are categorized in terms of level of access control or etc. So on the basis of functional similarity as well, hierarchy can be defined. So then we have location based applications. In this what happens, the GPS etc. positioning applications are taken into consideration. Say for example, if we have a GPS support, then what would be my routing strategies in that manner. Then we are having quality of service based. This is something that is mostly associated with multimedia traffic or any real-time application, which is in which quality is of major importance, and delay is, it cannot handle delays. So delays have to be taken care of. So these are the different routing protocol categorization. There are so many number of protocols, routing protocols there on the basis of different applications, on the basis of different network structures or functions that a network support have. Now let's study about the most basic one, routing protocol, that is flooding. In flooding what happens, it is obviously needless to say it's applicable to the flat based network structure, that is all the nodes are homogeneous in nature, be it software or hardware design. So in this what happens, the packets are sent to all its neighbors. Whenever a node is having a packet, it will send it to all its neighbors. For example, in this figure as we can see that A is the sender and it has to send a packet to G. So now how the packet is going to get routed from the node A to G? There can be different strategies to find out the shortest path and make the packet available at the node G. But according to flooding what happens, the node A will try to find out who are their neighbors. Neighbors means one first hop nodes in one hop connectivity. So it discovers that B is the only neighbor it has, so it will forward its packet to B. Now B is having a large neighbor set. It's having D, F, E and C as its neighbors. So what happens, it will make copies of that same packet and it will send to all these nodes. So as we can see that there is a lot of wastage of the network bandwidth. Also, what happens when multiple copies are generated, there is a good chance that some nodes might get more than one copy with respect to time. Now, it can happen like some of the packets that it is receiving, some of the copies might get corrupted or whatever. But the thing is, its buffer is also getting congested with having the similar packets. Like in the figure as we have seen that in node F, how many copies we are getting? We are getting 3 copies of the same data. So this type of phenomena is called data implosion. And obviously we don't have any privacy, no data privacy, and network as we can see that it can get heavily congested. And since there is no cluster, if we try to apply such application throughout the network, it will be like a wastage of bandwidth and so much of network resources, right? So it is recommendable to use in a limited scope. Maybe we can use it within a cluster or within a small group or some nodes, a small set of nodes, then it will be working perfectly fine. Now, gossiping. It is another improved version. In this what happens, the data is forwarded to a randomly chosen nodes, unlike the flooding mechanism. In flooding, a node will forward to all its neighbors the same copy of the data, but here what happens, just to optimize the network bandwidth, the data gets forwarded to only one randomly chosen neighbor. So apparently it avoids data implosion. But what is the drawback it's associated with is that since time is taken to choose which neighbor it has to select for forwarding the data, there is a little time gap, or we can say that due to restricted forwarding, the data that could have been reached, as you can see that from A to D, the shortest path is of 2 hop, but it is reaching in a 3 hop time instant. So there is a delay in D getting the data, and also at each node this delay is mainly introduced. Why? Because of decision regarding the choice of neighbor. Now, one thing that happens here is once a neighbor is chosen, it will never be chosen again in the current data cycle, just to avoid looping. We have discussed about this, that a good routing protocol is one that should not fall into loops. So just to avoid loops, the data will not be forwarded to the initiator. Next we have SPIN. SPIN stands for Sensor Protocol for Information via Negotiation. So what happened in flooding and gossiping is that data was being forwarded to its neighbor, whether they are asking for the data or not, whether they are ready to relay the data forward or not, right? So in this case, what SPIN is doing is, though it's a protocol for the flat architecture only, but it's first trying to negotiate with its neighbors that whether they want the data actually or not. If they deny, the data will not get forwarded to that particular neighbor. It's not like gossiping that randomly any of the nodes will be chosen. So it's upon the neighbors to have the decision of choice of like whether they will have the data or not, or discard it. So there is obviously a negotiation policy we have here. Then another good thing with SPIN is that it will not send the data directly. It will rather try to send the metadata. Metadata is something, the information that the actual data is going to hold. So a metadata is being sent if the neighbor finds that the data is required for it. Then what it will do, it will send a positive acknowledgement back to it in form of a data request. Now only those neighbors who have requested the data, maybe one or more than one of its neighbors, so those nodes will get the data. And here the constraint is that the node, obviously it should be knowing that how many neighbors it has and all those things, the topological informations. And obviously the redundant transmission is largely avoided, and it reduces energy consumption, especially compared to flooding and gossiping. Now, how SPIN works? SPIN has 3 types of packets. The advertisement packet, that is the metadata. It's normally of 16 bytes, but it can be adjusted accordingly. So this advertisement packet is like a metadata which is flooded to all its neighbors. Remember that we are using the word flood here. It means that the advertisement will go to each and every neighbor. Okay. Now once advertised, then we have a request packet. The nodes that are requested to have the data, they will be replying with a REQ packet. Then once there is a handshaking, the negotiation is being done, then the data packet goes. So the data will be a large, it can be 500 bytes or even more than that. Okay. Now, but there is a disadvantage associated with SPIN, even with the SPIN. What it is? It's that the data advertisement does not guarantee the delivery of data. Yes, it's very true, because if some node in some subset of the network might be waiting for the data, but its parent node might have just rejected because it doesn't require the data. So it will not reach to the child node. Let's understand this with an example. Here in figure A, we can see that node A is having 2 neighbors, C and B, right? So advertisement packet, ADV packet is going to both the protocol, both the nodes. Now, say for example, C is not interested in data, but B is interested. So, it responds, as you can see in figure B, it responds back with the REQ packet. Once B is having the hold of the data, B will advertise to its peers that are connected to it the advertisement, and this process will go on. But let's say if some node in the subset that is C is forming, the network subset that C is forming, if some node in its part requires the data, but since C has rejected the request, those nodes will never get hold of the data. So, this is a drawback of spin. And apart from this, the application, according to what application, the nature of application, the demand of application, the purpose of application is, the network protocol designers can design the protocols accordingly. It can be obviously a combination, some combination of this or other existing protocols, etc. Now, since we have a good introduction of how routing happens in wireless sensor network, now let's come to the sensing model. It's a prime feature as the wireless sensor network. The word sensor comes, it means that sensing is a very important characteristic of the sensors besides transmission, reception, computation, that is processing, etc. Okay, so before understanding, before going towards the sensing models, it's important to understand there is a difference between communication coverage and the sensing coverage. Sensing coverage is something that guarantees data coverage. That is, it can be explained as effective area that is under monitoration, right? If the radius, the sensing radius is say RS, then every area, every point of the region of interest coming under that radius, that area will get covered. That is, the data from that part of environment will get recorded. Okay, but what is communication radius? Communication radius that imparts communication coverage is basically for connectivity. Say if the communication area of two nodes are overlapping with each other, it means that communication is feasible between those two nodes. Okay, it means that those two nodes are connected, they are connected for transmitting or receiving data. Now, if we want to increase the complexity level a little more, we can say that instead of communication radius, we can talk about transmission radius and reception radius. But for timing, let's call it communication radius, bunched up into one. And so, I think it's clear by now that there is a difference between the communication radius and the sensing radius. One is for data coverage and the other is for connectivity. Okay. So, now some symbols are there which we need to know. The first one is ZIT. It is a time dependent measurement of sensor I. It shows that if a sensor is going to record some data, it will be denoted by ZI with respect to time t. Okay. Then we have the variable xt. Now this is the parameter that is going to get measured. It can be the environmental temperature or the intensity of surrounding light or some target identification, humidity level, anything. Okay, so these are the parameters that are dynamically changing. So these are the dynamic network parameters, you can say. Then we have lambda I, again with respect to time t. They refer to the characteristic of the sensor node I, which is relatively stable. Relatively stable in the sense what type of modality the sensor node has. Say for example, if we have a sensor node that is there for sensing the temperature or sensing the intensity of light. So, if it's a light sensor, it will not obviously sense the environment temperature like that. So, sensor modality, even sensor position, what is the XY location, the coordinate details. Also, it can be the power, remaining power, or the maximum transmission power level, etc. So, lambda values are what? They are the sensor characteristics, and x values are the ones that are going to get measured. Now, If we put all these things together into a mathematical model, it can be written as a function, some function say h, of the measurements, the dynamic part, and the sensor characteristics, that is the static part, that are relatively stable. Now, if we have this model with us, then just to try, I'm trying to explain it a little further. If we take up a special case over here and we explain, we split the function h into function f of obviously those two dynamic and the static parameters, along with a noise parameter as well. Now this because sensors are very vulnerable to noise, because it's wireless channel, so it will be vulnerable to noise, disturbances, etc. So whatever temperature, whatever data it's going to sense, there will be some impact of noise. Okay. So this noise can be some Gaussian noise. Normally wide Gaussian noise is taken into consideration for simulation purpose. So this formula gives a good idea of how a sensing model can be developed and what are the factors that impacts on the sensed data. Now let's understand this more by doing a small case study. Say we are trying to localize a target. The application is target localization, a stationary target localization, in which the assumptions that we make are our sensors that are going to do this, they are all stationary, they are not moving, no mobility, and obviously time variant, because with respect to time the details will be fetched. And what type of sensors they are? They are acoustic sensors, that is they measure the amplitude of sound of the signal, right? On the basis of measurement of the intensity of sound, they are going to find out where the location of the target is. Okay. Then we have the state vector. State vector is the unknown target position, the x and y targets, target locations. Okay. Then we have the sensor characteristic, the lambda I values. Here we have a zeta value, it is the known sensor position. We can see that it is zeta I, it means the sensor position of the ith sensor node. And obviously we have a known additive noise variance. Okay. So then now we will find out how to model a real time case study with all these parameters. Thank you. Welcome back. We were talking about a real-time case study. In continuation to that, we make another important assumption that the sensors are allowed to use acoustic signals, and these signals are isotropically propagating. Okay, that is, they are propagating in the same intensity in all directions. Now, to model this application of stationary target localization, it can be done as in this equation, highlighted equation. So here what we can see that Zi, as usual, it is our sensed data, that is the data that we are getting, it can be a numeric data or whatever. Ai is the random variable, it represents the amplitude of the signal at the target, that is the amplitude of the sound. Alpha is a known attenuation coefficient. This is a path loss exponent. Remember that as our environment condition is, if it is free of hindrances and it's a free space, it's giving free space for communication, then this value of path loss exponent is usually 2, and it ranges to 5 or maybe some value slightly above 5, and this value is governed by the obstacles. More and more obstacles, the value of alpha will tend to increase. Okay. And then we have our the Gaussian variance, the Gaussian white noise, and the variance is taken to be sigma I square. Okay. And it's needless to say that the double bars x minus zeta I raised to power alpha by 2, it means that it's a Euclidean distance of the sensor position and the target localization. Now come to actual models. The first is binary sensing model. This is a very basic model, a benchmark model. In this, what happens? First, let's see the basic features that we have. Here, a sensor node S is taken, and it's the disk is of fixed radius, and its area means that we are talking about the sensing area, obviously the area that is covering the sensed data. Okay. Now, any event E, if occurs at a point, some point P, and if this location of this point P is within this disk, then we say that it can be sensed with a probability of 1. For other possibilities, it is always 0. So, it's a very discrete value that whenever some event is happening within the communication, within the sensing radius, not the communication radius, remember, the sensing radius, then it is going to get recorded with probability 1, otherwise it is just going to get discarded. Okay. So, this is what the model says mathematically. Obviously, the drawback is that it's a very deterministic model, because the first thing is the circumference that we are talking about, the disk here, the disk is not very discrete one. At the edges especially, the power, the transmission power, say the level of battery power of the sensor, it always gets fluctuated. Okay. So, there is a lot of imprecision in this model due to hardware malfunction and decay over time, and also the sensing coverage, the sensor coverage, it is not a perfect circle, because at the edge it is going to fluctuate. For this, let us take up another model, the probabilistic sensing model. In this, what happens? We have the same old sensor with the sensing radius r, but now what we are doing, we are taking a minimum power level and a maximum power level of the sensor, and accordingly we are getting a donut kind formation, in which the innermost ring, it signifies the minimum transmission level. That is, what if the sensor is at some point of time is using its minimum power level, so it's obviously getting less than what the average sensing radius RS is. Okay, and the outermost is like whatever its average radius RS is, it can be even more than that. So, the outermost ring is showing the maximum impact of maximum transmission power. Okay. So, this donut formation of sensing region is giving new parameters RU. This is the uncertain area, the radius of the uncertain area. Okay. So, in addition to the inner area, that is the region with radius RS minus RU, which ensures in this area whatever event is going to happen, it will be recorded with 100% probability, that is probability 1, it will get recorded. Okay. And in the exterior, that is anything, the region in the region that is outside RS plus RU, anything that is there outside the area of the sensing radius, then it will not get recorded. And then obviously we have the uncertain area, which is of very important, that what happens in this area, whenever some event occurs, it will get recorded with a probability that decays exponentially with distance. Now, let us see mathematically what it actually means. So, in this figure you can see that it is properly labeled. The shaded area, it is the uncertain region, interior region is clearly visible, and anything apart from the uncertain and exterior region is the interior, and uncertain region is your exterior region, the outside region. So, mathematically we can see that the second row of the equation, we can see that it is given by lambda e to the power minus lambda beta. This is the exponential distribution, because the distance, it's getting exponentially decreasing with the distance metric. So it's the very commonly used exponential distribution. And be very careful about the distance, that the Euclidean distance between S and P. S is the position of the sensor node, and P is the position of the point P where the event is getting triggered. Okay, so at the Euclidean distance, it should be lying within Rs minus Ru if it is to be getting recorded with a probability 1. If it is between Rs minus Ru and Rs plus Ru, then it will be in the uncertain region and it will get recorded with a certain exponentially degrading probability, and in other cases it won't be recorded at all. Okay. So lambda is our rate parameter, and beta is the distance difference of the distances. So this is our probabilistic sensing model. So accordingly, the probabilistic sensing model, or whatever the binary model, can be applied as per the requirements. Now let's come to the mobility part. We know that the sensors, it's a very prominent feature of the wireless sensor networks, because there are actuators that are more powerful sensors, having better battery backup and higher processing capabilities, etc. So such actuators, they are often deployed to check for the requirements, any network impediments, etc., or to provide wireless charging to the sensor nodes that are deployed, the static sensor nodes. So not even the case of actuator is concerned. Also, there is always a actuation unit that is embedded with a sensor node. So whenever it is required, it can be like activated, they can be brought into use. So what are the different objectives we have to be careful of is, while designing or while taking up a mobility model, we should know that it should have the capability of resembling the real life movement. Okay, real life movement, it can be the movement of students, if you want to record the movement of the students in a campus, in the college campus, or it can be animal monitoring in a natural habitat, right, or the rescue squad motion in a disaster area, etc. So in some of the applications, the mobility model that is being developed should be able to simulate. What is the next point? It's that it should be simple enough to get simulated and analyzed, because before applying any model, obviously we have to simulate it to record, to pre-record rather, its performance. Okay. So it should be simple. It should ease the task of analysis and optimize the performance of several sensor networking protocols, because be it routing or be it clustering or any other energy aware protocols, whenever we have sensors with the mobility feature, it means that a challenge, one more challenge is getting introduced into the scenario, right? So now let's take up the different forms of mobility. Okay. It can be node mobility. The nodes that are deployed, they are mobile, or it can be, say, the sink is mobile. Sink, that is a local cluster head or local actuators that are there to monitor, to record the sensor performances. So there is a possible that those sinks are mobile. Even the event mobility is one more possibility. Event mobility means that any event that is getting triggered, the location obviously is not fixed. It can be at some location, it can be some other location as well. So the event can also happen time to time at different locations. So this is event mobility. And one thing that is important to note that when we are talking about node mobility, there can be mobility in some applications and there may not be in some other applications. For example, in environmental monitoring, if we are talking of, there might not be any mobility required, but if we are doing some kind of research with the natural habitat, then obviously what happens, the animals are there, they are all moving. So if we have to monitor the natural habitat or even the wildlife there, nodes are attached to those cattle, and as they move, mobility comes, right. So there can be different applications, and accordingly node mobility get introduced. Sync mobility, when we are talking about sync mobility, means that the actuator is mobile. So there is some challenges that get introduced into this type of mobility. It's that whenever actuator is mobile, it means that it can go to the concerned sensor node or sensor nodes, a set of nodes obviously, and get the data, fetch it from there. But if its mobility pattern is not properly, it's not optimally set, then it might visit to some area where the nodes are not giving proper data or something, right. So its mobility pattern should be predetermined, should be optimally determined in advance, okay. And even if it's a random movement of the sync, still some routing protocols should be well equipped with such actuators. Now let's visit different categorization of mobility models. The first is random waypoint model and random direction model. As the name goes, both these models are they are like intentional model. In this, what happens, the target location is randomly located, and the nodes they know that they have to reach that randomly selected position, okay. Then we have Brownian motion. In Brownian motion, it's an instance of unintentional movement. Then we have map based model, where certain restrictions are certain constraints are put, and group based model, which is it's taken up so many times in context of sensor networking, because sensor network mostly work in hierarchy, mostly work in clusters, and a group based model is it's a kind of very much realistic model, and we can say that it's a hybrid combination of all these models also, okay. So now let's see one by one. The random waypoint model. So here, as just told, that in this what happens, a node first selects a random destination, that is a waypoint, within the deployment region. Obviously the region, say the region is R, and once the destination is fixed, the destination point can be anywhere. It can be near, it can be far, it can be at the border, or it can be at the core, it can be anywhere. So once it is located, it fixed, the only function of that sensor node with respect to its mobility pattern is that to reach to that position, and once it's reached, then again this process will get continued. Now this is a very simple model, and mostly in S2 GlomoSim simulators they support, they have this inbuilt characteristic in them, mobility model in them. And the velocity that is chosen, that can be controlled obviously. It's in the interval of Vmin and Vmax. So the nodes can randomly choose a velocity, they are randomly choosing the destination point, and they are starting their movement, okay. Now here one problem that comes is the entire region is not spanned. The spanning, the movement of the sensor nodes is very localized. It's localized around the core somewhere. So just to avoid this, we have another mobility model, that is random direction model. In this, what happens, instead of choosing randomly destination point, randomly choice of interval, choice of sector is being done in this case. That is, any node that chooses a direction uniformly at random in the interval 0 and 2 pi. So the entire region R is now divided into sectors, okay. Now the sectors are spanning from 0 to 2 pi, and accordingly within a particular sector it chooses as its destination. So in that particular sector, whatever the largest distance is, it will move, it will tend to move towards that. That is, the nodes are now exactly moving to, till the border of the region in that particular sector, okay, in that particular direction. So all the moves, all the sensor movements, etc., they are going to exactly the border, and once they hit the border, they get bounced back to their original point. And similarly, this entire thing is continued to get a random mobility. Okay. So again, the velocity is same as in case of random waypoint model. Here also there is a Vmin and Vmax, the velocity minimum and maximum levels, so they can choose. But now, since what happening is the sensor nodes are hitting the boundary, so the spanning is like very uniform throughout the region. Because of this, it avoids the border effect that was previously there with random waypoint model. However, both the models, be it random waypoint model or random direction model, both these models they are what they are intentional models, because the destination point, be it xy coordinate or the destination sector, it's known in advance. Okay. So, but what happens if some application, in some application there can be some situation where the destination is not known. So the movement will be in such cases unintentional movement. So this type of movement pattern can be well provided by, can be well simulated by Brownian motion model. In this, what happens, as in the figure we can see that it's a zigzag pattern. Okay. So here what happens, the position of the node, if it's known at a point of time, then whether the movement will be in left or in right 1 unit or whatever the unit is, or up or down or wherever it has to go, the probability is defined for that. So accordingly, according to the probability, it will move. But if you are talking about ideal Brownian motion, it's like 50% chance that it will go to the negative direction and 50% chance that it will go to the positive direction. Okay. So the movement is equiprobable in this case. And for this, Brownian motion mobility model is governed by 3 parameters. The first is P stat, P move, and M. P stat is what? This is a probability that a node remains stationary for the entire simulation time. With what fraction of time the node is going to be stationed, it will not move for its entire functional lifetime. P move is the probability that a node is going to move. There is a movement probability, in short. And since our node is now moving, then we are also interested to know what is the rate, the speed, or we can say the rate of its movement. Okay, somewhat it models the velocity. So if a node is moving at step I, its position at step I plus 1 is chosen uniformly at random according to the probability that is built up. So this model is completely probabilistic. Okay. Now let's come to map-based model. Now here what happens, what we can see here, that certain restrictions are there in map-based models. Rules are there that we call traffic rules. Okay. So and whenever we are talking about traffic rules, traffic patterns, movement patterns will come up, then map setup, etc., all these things will be there. Unlike the previous models, Brownian motion and random waypoint and direction model, in this there were no constraints, no such constraints of that governs the movement pattern. So here this is what in this nodes are constrained to move within specified paths. Say there are sidewalks or there are some car lanes, 8 lanes, 6 lanes, and how these type of situations they come up. Obviously first we have to set up the map. The map can be a real map or it can be a randomly developed map. Okay, so two things that it should have. The first is allowable movements, where the cars can move, where it cannot. So this should be there, and the path layouts. Obviously, what are the dimensions of the paths? That is the 8-lane on a 6-lane route or 2-lane route, etc. Okay, then obviously there will be some rules with the type of movement. We have specific rules, and initially what will be the condition of the roads, where the nodes are already there, randomly set up, etc. So a lot of setup things are there when we are talking about map based mobility. So let's see some of the map based mobility. The first being freeway map based mobility model. So here in this case, what happens, it is developed to resemble the movement of cars on the freeways. Freeways are like straight line roads, or whatever, there can be some movements or some bends, etc. But these roads are open infinitely on both the ends. That's why the name freeway. Okay. Now in each freeway there can be different number of lanes running in both direction infinitely, and the nodes that are randomly located on freeway, they have random velocity chosen within a range or whatever, or they can maintain some average speed, etc. The constraint that we have in this model is that if on a particular lane two vehicles are moving, then the second vehicle, the following vehicle, will not overcome the first vehicle, and it will maintain a distance which is known as a safety distance. So this is the only constraint that freeway map based mobility model has. Otherwise it's just straight line roads or whatever, there can be some bends, etc., but they are infinitely spanned both ends. Okay, so it's the only constraint we have. Then let's move to another one, Manhattan map based mobility model. Here the constraints are a little bit complex. Here what we have horizontal and vertical streets, and since we have vertical and horizontal streets, it means that there will be junctions, and with junctions comes decision making. That is, whenever a vehicle reaches a junction, it should have some decision making capability given to them, or maybe their movement is governed by some probability distribution, etc. That governs that whether they should turn whichever way they want, right? And obviously there are some other conditions like don't care conditions, etc. Okay, so and the safety distance parameter will always be there, because Manhattan map model is more it's a better model than the freeway one, so it will have the features of the freeway as well. Then we have obstacle map based mobility model. In this model what happens, obstacle generation phase is an additional one that comes up. The obstacles can be random, or they can be set up according to the maps, that the real maps, etc. And a very interesting feature over here is that in obstacle map based mobility model, what happens, the obstacles can be intentionally set in a manner to check out the impact of radio propagation that we talked before, how a particular type of propagation is going to work in a given surrounding, to study the impact of it. Obstacle map based mobility model is a very powerful one. Then we have group based mobility model. As told before, that in this model the sensors are collaborated, they are bunched up in small groups. Each group will have group leaders, and this type of scenarios are can be found in say in battlefield applications, where the military movements are generally in troops, most of them, or the tourists are moving in a city, if you want to track their movement. So it's always the group based one, because if you are talking about the tourist movement, there is a tourist guide, so all are following that guide. So here also we have in this model there is a group leader, and the group leader moves according to any one of the previous models. Okay, It can be the any map-based model or random models, intentional, unintentional models, etc. So whatever the pattern of the group leader is, the members are going to follow it. Okay, and the speed and direction are obviously random, and whatever the speed and direction the leader will have, the group members will follow the same. And one interesting thing is that whenever the two groups, any two groups, they tend to cross each other, in that case what happens, there can be some members leaving the group and some members might be joining some other group. There is a flexibility in this model, and this can be done as per the decisions that they make, the members are making, or it can be done with a with some certain kind of probability. So this was all about the mobility models that are there for random environments, for city-based environment, for group mobility patterns, etc. So later we'll study more on these aspects. Thank you.
On that note, I would like to thank ma'am for this very enriching discussion, and thank you dear friends for watching our show. Stay tuned and keep watching. Thank you.